Yeah, so hope my screen is visible, right?
Yes, sir.
Okay. So we have covered a long roadmap across in the form of supervised learning. So just to give you a very brief overview about where we started and where we land up is, so if you remember that we started with finally finding an unknown target function.
Sir, sorry to interrupt. This is Shubhadeep here. I got
Yeah,
delayed. Today is my scribe. I got delayed by a couple of minutes.
yeah, sure. So please try to take the scribes for today.
Yeah, today I will take. It's my
Sure.
turn.
Thank you.
Thank
So we started off with finding this unknown target function, but actually what we are provided with is basically a set of training examples. So we are provided with example x1 and its class y1. So that's why we call it as a supervised learning, because there is a teacher which provides you the level values or the class values also according with the attributes that are given to it. So we call it as a training examples. So then depending on these training examples, we started to go for a learning algorithm, which basically takes as input not only the training example, but also a set of hypotheses. And finally, when we come up with this learning algorithm, we got a classifier. So this classifier is basically the outcome, which may be in terms of a program. And then with this classifier, so if you fed in a particular new attributes, then this classifier is able to give you a class. So that is the overall roadmap that we came across in the supervised learning framework. Now, if you recollect that in this framework, we also learned certain kind of algorithms such as decision tree learning algorithm, where your hypothesis set, so decision tree learning, so let me call the algorithm name that we have learned is ID3, for example. So your in that case, your hypothesis set is basically decision set of decision trees. We also learned certain kind of perceptron learning algorithms as well as back propagation algorithms, and there your hypothesis set was restricted to neural networks. We also learned something called k nearest neighbor, and in this case, in that instance based learning, so your hypothesis set is limited to the fact that the choice of k, and since it's non parametric, so you got any kind of hypothesis set from here to classify this with respect to the choice of k and the distance measures. And finally, also we have seen some other algorithms like support vector machines, where your hypothesis set, it's a linear classifier. So hypothesis set is basically the set of weights that represents a hyperplane. So a hyperplane. So with this backdrop in our mind, so with this backdrop in our mind, what we tried to find now is that though we are given a set of classifiers, and if you try to look pictorially how this classifier look like, I mean the decision boundaries of this classifier, suppose you have certain points like plus 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 and some points like minus minus minus. Now if you go for a linear classifier or a linear predictor, sometimes the support vector machine tries to draw a line in between this, provided the margin becomes widest. So that is how we do in support vector machines. When we go for perceptron learning algorithms, so we also try to do such kind of a linear classifications with the perceptron learning algorithms. So there also we try to draw a classifier. Maybe your classifier could be like this, in that case, perceptron learning algorithms. In decision tree, when you go for it, so this is perceptron learning algorithm or any kind of linear predictors, I would say. So when we go for decision tree based learning algorithm, so there you have again, let's say these set of points, which are my training examples. Then your decision tree based learning algorithm tries to do it in terms of, as you know, it tries to find out certain values beyond which it will classify in terms of the decision trees, and it finds such kind of decision boundaries. When you go for multi-layered perceptrons or neural network in more generic sense, so there again with this same set of points, so your neural network may classify this as some kind of this kind of an arbitrary boundary where there are two depth hidden layers can do this to such kind of a classification. So all this, so we also have this KNN kind of a classification. So if you go for the KNN, so this is neural network, how do it classify? And if you go for the KNN, so for example, KNN may do it this way, right? After condensing and all, it will do it in this way. So if you go for KNN, so as you can see, we have many such approaches to follow, and each of the approach will try to give you certain kind of decision boundaries that among which you need to choose finally that which is the best among all. So therefore, in today's lecture, we will primarily to focus that how do we evaluate that how good or bad is our classifier that we finally learned through our algorithm. So this will kind of the last lecture in this traditional series of supervised learning where there are multiple methods we have learned, but finally we need to produce that how much good or bad is our classifier that we have learned. So to go by that, so let us start that analysis that how good or bad our classifier is. So therefore, first of all, we need to find out what are the measures of telling something of evaluating the classifier. And as you can see that one of the measures is that we can find a performance, that how good or bad, how accurately I am trying to classify the unknown training test data that is given to me. So I need to find out certain kind of performance metrics depending on which I will say some classifier is good and some classifier is bad. Then how do we estimate such metrics? So we need to find out some methods to estimate such metrics. And third, how do we compare with respect to these estimated metrics, the different models of classifications that we get? So this indeed is the outline of our lecture that I will try to follow today. So first of all, let us concentrate on how we can design a particular performance metrics. So one of the traditional performance metrics that people use is sometimes called as confusion metrics. So basically what it does is that, so what we will do that either from the given set of training data, either we keep, let's say some m number of data, let's put it in capital M number of data as test data. Either this m number of data we separate out from the training set as you have done in many of your projects, or maybe it is a test data where you know the answer, but for testing you will test on them. So as you can see, the confusion matrix basically will try to then, with respect to this M data, suppose we are doing a two-class classification. So suppose with respect to this M data, this side I will plot actual, but would say the actual classes. And let's say my actual class are yes and no. And here on this side, I will try to plot my predicted classes. Again, the predicted class could be yes or no. And depending on that, I will try to fill up these two tables where this entry this entry and this entry are the number of such test example false in each of this category, which means that suppose the actual class for this m test data I have, if I have tested in my classifier, the actual class was yes, I predicted yes, then I will call it as a true positive. So I made it positive class, which is also the actual one, it's true. Similarly, if the actual class says no, and also my predicted class says no, so that means I have done true classification, and this is a true negative. The others are actually I am not doing well. That means when actual class will say for this number of data, actual class says yes, I am doing it bad. So this class I will say it as false negative, because I am giving negative answer for that, which is false. Here also, I am giving a positive answer for that, which in the actual class should not be positive. So it's a false positive. So this table is basically computed with respect to the predicted class and actual class over the m test data. And as you can see that the number of true positive cases plus the number of false negative cases plus the number of false positive plus the number of true negative is obviously will be equal to m. That is the number of test data that I am trying to experiment with. Clear this confusion matrix?
Yes, sir.
Yes, sir.
Good. So this is the basis of all our estimation or performance that we will try to measure. So one of the metric people typically follow, but before that, let me also do it. So we are doing it in a 2 class. As you can see, it's a 2 cross 2 matrix for 2 class. If you go for a K class, so it will be nothing but such kind of K cross K matrix, as you can see easily by this figure, that here it will be predicted class 1, predicted class 2 up to predicted class K. Here will be actual class 1, actual class 2 up to actual class K. And depending on that, you can easily see only these fields are correct. Only the diagonal fields are correct, right? I hope you can understand what I'm meaning. Because only the diagonal field, the predicted class and the actual class number matches. The rest are actually wrong. In our case, you can see this diagonal green is the correct one, the red are the wrongs. So this is a K cross K matrix, to be more general confusion metric definition wise. Now people try to formulate such kind of measures that they first try to find out what is called as accuracy. As the name suggests, you can easily see, yeah.
Sir, in case of K cross K matrix, here but the diagonal elements are the true elements. So these are two positives. But then what will be the name of the other entries? In 2 by 2, we are referencing them as false negative or false positive.
So I mean, so if I refer it as A, B, C, D, would it matter? So, and then I say that A plus B plus C plus D equal to M.
Okay.
It's the number, right? It's the number of those many cases. So here only in this diagonal actually is the correct, your classifier is predicting correctly. The rest your classifier are not predicting correctly.
Okay.
Okay. So this is, I just mentioned it so that it becomes easier for you to understand this meaning, because now I will define it with respect to this. Say, suppose I define something, let's say A by A plus B. It's very difficult to infer what is happening. If I say TP by TP plus Fn, then you will easily, and you can easily argue that what is happening. That's why I gave a name which is realistic. It could be done well for 2 classes. For multi classes, such naming could not be done. Then you have to say TP1, TP2 up to TPK. Correct? Then true negative is also here. If I do it for a 2 class, it will be TP1 and TP2.
Okay.
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 So accuracy is basically, as you can see, accurate means how much I am classifying correctly. So therefore, the sum of the diagonal elements divided by everything, that is in our case m, the sum of total elements. So here for two class classification, it is basically the sum of true positive plus true negative, that is my correct classification, divided by m, which is basically the sum of all. As you can understand, my m comes from here. So this is the accuracy of my predicted classifier with respect to my test data. Now here you can, if you think a little bit carefully, you can immediately find out one particular fallacy of this matrix. Suppose, for example, my data, the test data is a little bit biased towards a particular class. Suppose in my test data, there are 9990 data which are labeled as positive, and there are only 10 data which are labeled as negative in my test data. Correctly, these are the labels, actual classes. Now see, suppose your classifier is designed in such a way that it says everything to be positive, positive for all. So therefore, you can easily sense now, therefore, the accuracy by your classifier is basically 99.9%, right? Because it's the number of, see, the classes are making correctly with respect to the total number of classes, the number of true positives, true negatives, it is nothing true negative because I am not making anything as negative. So all the true positive divided by the total number of instances that I have. So therefore, this is biased to the test data. So accuracy does not reveal such a good thing unless your test data is also little bit distributed in a good manner. So this is one of the
accuracy you are measuring over here is based on this is based on the test data, right? This 9990 and 10 is a test data, right?
yes. So you are given 9990 test data attributes with level positive. So without knowing this, you just run your classifier over this 10,000 data. So when you run your classifier, suppose your classifier blindly makes everything positive. So then also your accuracy is very good. But does something which is making blindly everything positive, do you think it's a good classifier? It's not a good.
According to just one test data, we cannot generalize the things over here. Like maybe in the some other example where the negative
yeah, so what you are referring to,
like,
that's what correct. What you are referring to, the solution is the fact that the distribution of the test data is actually what matters. When you are saying not only one test data, what do you mean? You mean the distribution of these positive and negative classes, right?
yes,
Because suppose in another test data you get 1,000 positive classes, then also your thing says it's 100% accurate. So distribution between positive and negative classes matter. So therefore, accuracy only cannot be the sole classification criteria, sole guidance criteria of some classifier is good or bad. Then people along the line also thought about something called as a precision. I hope you have used some of the project groups have already used it unknowingly or maybe knowingly. So precision is nothing but the number of true positive divided by the number of true positive plus false positive. Sorry. So as you can see, the name precision says that how many of them I am categorizing in terms of a particular class with respect to my prediction, how much precise I am. So when I predict yes for something, how much precise I am for that yes. So whichever I have classified correctly divided by the total number of yes predictions is the percentage of my prediction being precise. So we give this as something called P. The other thing people also try to see is what is called recall. We call it as R as well. So it is nothing but you recall with respect to the actual class. So with respect to the actual class, which is yes, how good are you recalling for the actual class? So it is basically the number of true positive divided by the number of true positive plus false negative. the row wise. So I am how much well I am recalling my prediction with respect to an actual class. So these are the primary dominant metrics that people use to classify, to judge the performance of a classifier. However, both of them has some merits and demerits. So this precision and recall, both of them has some merits and demerits. So sometimes people, yeah.
In a particular row, we will have just one entry, no? Because
I am saying the row of a confusion matrix.
okay.
So you just look at this formula.
So
it's not, yeah.
So we are not considering the true negatives.
Correct. I will come. Gradually, I will come. See, accuracy is not a good term. Precision recall individually may not be good. That's why I will move to slightly different. Then I will come to a generic one. So, as your friend suggested, that precision and recall sometimes individually also they do not have some merits and demerits. So people try to use a combination between precision and recall, which they called as EPS score. So what the EPS score says is basically it's a harmonic mean of precision and recall. So it's basically 1 by F, half of 1 by precision plus 1 by recall, and it eventually translates to F equal to 2 PR by P plus R. So that means that if you try to simplify the whole thing, so this whole thing with respect to true positive and true false positive and all that. So if you try to simplify, then it will come as 2 into this divided by true positive, false negative, false positive. Just deciphering this P and R, because I know my P is this and my R is this. I'm just putting it there, nothing else.
So,
yeah.
So can you please just explain the recall again? Just the intention behind that again.
Oh, see, recall means that with respect to a particular actual class, how well you are recalling. How well you are recalling the actual class correctly. So with respect to a particular actual class, how well it is recalling means how well it is giving correct with respect to all other miscalls. Okay, that is what the recall naming comes from. So see, Urvashi, it is nothing but just a naming of that. Ultimately, this is a mathematical equation that we will invoke finally.
Yes, sir.
Okay, so that's what. But people mostly sometimes go with also the EPS score factor as well. And as your friend correctly pointed out, is this factor that all of them are a little bit biased. As you can see that your precision is biased towards true positive, as well as you can easily see, I am doing a precision with respect to these two only. So I am biased with true positive and false positive. Similarly, your recall is biased with true positive and false negative. And your EPS score is biased with true positive, false negative, and false positive. So, as your friend suggested, that we are ignoring true negative, totally ignore. Therefore, two things people have done. One, so one of the solutions become like this. So one, people try to give a weighted accuracy. So when I say I will give a weighted accuracy, so let me call it WA. So what they do, they try to put a weight with respect to true positive plus a weight with respect to true negative divided by, it's just the accuracy with, I am putting a little bit of weight on everything, How does it help? See, now depending on my weight, I can construct anything. If you have to construct the precision, your precision is basically TP divided by TP plus FP. So therefore, you will keep W1 and W3 as 1, W2 and W4 as 0. If you have to construct recall, you can easily see that you will keep W1 and W3, sorry, W1 and W4 as 1, W2 and W3, am I correct? No, I don't think so. W1 should be 0, W2 should be 1. So W2, W1 and W3 should be 0. And similarly, you can easily construct for F score, you can easily construct the weights accordingly to get this thing. So this is one solutions that people try to give. The other solution that people try to give is that associate a cost with the confusion matrix. So what do we mean by a cost? That depending on the scenario, whether true positive giving is more fatal or false positive giving is more fatal or false negative giving is more fatal, depending on that, they try to predict a cost for each of the operations. So yes given yes. So this given yes means this is the actual class level and this is your predicted class level. So as you can see, there will be 4 such cases. Yes given no, which is basically our, so actually it is no, I am predicting yes falsely, so it's a false positive. So it's the true positive costs. Similarly, cost of no given yes, which is basically a false negative cost, and the cost of no given no, which is basically true negative cost. So people also, instead of weight, as you can see that instead of weight, people also go for a cost. Actually, these two with respect to accuracy means the same. However, this gives you a handle because, for example, if you see that where false negative may be more costly and which occurrence false positive may be more costly. Suppose you are in a very strict security in vigilance bureau office where your fingerprint, if you put a fingerprint, correct person, identified person should come in. So there you can see you must have multiple higher level of penalty values for the people who are not authorized but coming in. That means which are actually should be no, but getting a yes from your classifier that sits on the door. On the other hand, suppose in a supermarket, suppose you get a discount with respect to giving your fingerprint, and here you see the false negative, one person will get more, a higher discount that he is not entitled to. So that is less fatal. So depending on that, people scenario wise, the problem that is going to be solved, people used to devise such cost metrics. So primarily these 3 things are followed. Apart from that, there are other factors like what is the ratio of false positives, what is the ratio of true positives and all that. And at the end, I will give you a reference. This is just a mathematical ratio operation. You can easily understand what do I mean.
So,
but let us just, yeah.
Sir, I think recall weights are wrong.
W4 should not be 1 because otherwise we would have considered a TN.
Yeah. So W1 and W2 should be 1. Yes, made a mistake. It should be W1 and W3. No, W2. Sorry.
W1, W2.
W2 and it is W3, W4. Correct. You are correct. So this is how we go for devising metrics. So then our next concern comes as we have started off with. So this is we have done. Our next concern, how do we estimate? What are the methods of estimating these metrics? So we use multiple things, and some of things you already know of because you have used in your project. So as you can see, as our project also tells you that plot your accuracy with respect to your sample size sometimes. So as we know, as we grow the sample size, you can easily understand your accuracy may behave like this, and sometimes later it will get saturated, let's say with a 95% accuracy. So these are my sample sizes. Suppose I give 10 square, I give 10 cube, I give 10 to the power 4, and so on. I move on. It saturates like this. And which is basically in machine learning terms, which we call it as a learning curve. Sometimes this learning curve is a good estimation that with respect to the sample size, how your methods are behaving. So it's a good estimation of that. So basically it is dependent upon, so as you see, the accuracy is always dependent upon the class distribution. Therefore, your method of estimation in this way is also dependent upon the class distribution factor. So you need to give a test into certain good distributed way so that both of the classes or even all the classes is good. It also depends on the size of training and test sets. Why so? Because if your training set is very thin, or rather the distribution of the training set is poor, then theoretically we will come to these notions a week maybe later. There are two things that we will get. I am trying to give you an intuition of these two things. So either my training set will bias my learning. That means whatever I see, what less I see, I will try to fit in. And this may not be in the actual scenario. It will bias my training estimate. So I will get a biased estimate for that case. The other thing, depending on this thin size of this, let's say our test data is very less. So I may get a variance of the observed metrics because this test data is so less that it does not represent at all the scenarios. So later we will just give theoretical insights that how do we control in our classifier, how do we theoretically say that the learned classifier, the bias versus variance factor, how do we estimate theoretically? But this has a strong correlation with respect to the class distribution as well as with respect to the training data that we have in our hand. And the final thing that we already introduced in the last slide, we need to also have methods for estimating the cost of misclassification.
So
the example that we
bias and variance again.
Yeah, so bias, I am saying, see, bias as the name suggests is the fact that, so let me give you a practical example of the bias. So in case of linear predictor, what do? You do this plus B, where B we say as a bias. What does this B has to do in your linear prediction? So suppose you think of a linear prediction. Suppose these are positive classes and these are negative classes, and your bias is basically shift these lines towards this side or this side, right? Because it's the threshold of the line. So what does it mean? It biased itself with respect to the input space, input training space that you have in your hand, that where should I push this line towards? Unless you use support vector machine where the bias is totally in the margin, middle of the margin. So bias gives you a fact that how much training data do you have, right? It is dependent on that, because in a support vector machine also, suppose I have only two data, one plus here, one minus here. So definitely in support vector, you will try to fit something which should be in between these two. Now, if in actual case, you see the datas are not like that, the datas are like this, then this is your bias. The actual one line should be like this way. So this is your bias that you have made due to this training data being thin, size of the training data being less. So intuitively, this is what we mean by bias. Okay.
And so the variance over here?
Yeah, the variance over here. So as you can see, though I represented it with respect to test data, but it has to do both with it. So variance is basically the estimation that you had made depending on the test data. You claim that this method of estimation has given me very good in classifier, but that may vary on the scenario unknown to you. That's why we call it a variance. But these are very rough intuitions. Just hold on this factor for a week. I will come back with very theoretical justification of this bias and variance trade-offs. So how can we trade off between bias and variance and can find a good estimation of our classifier? Okay. So this is how by definition or by intuition we try to mean it. However, so the model of estimations or the method of estimations that we are trying to see are dependent on these factors, but you know what to do in terms of the methods. So what you have done is you have used this kind of thing, right? 2/3 data for train, 1/3 data for test. Usually, given the training examples, I keep the test and training data in this category and do it, which is often known as, the method is often known as holdout. The second is very popular and you repeatedly use it, which we call as a cross validation. We have a K partition and you keep K-1 partition to train and the remaining K partition to test. So this, as you have used, it is known as cross validation. And sometimes we randomly take any other K-1 partitions and a separate kth partition for testing. A little bit variant term, I'm just introducing a term, we sometimes call it as a random subsampling. This comes from a statistical term. We repeatedly do holdout randomly over the 2/3 fraction of a data. So also random subsampling can also be used in this case. If you randomly do this, which K-1 partition, K-1 partition will you keep it as a training or which partition you will keep it as a testing. But from this random sampling, a new concept came, which is most popular use. It's a statistical concept, which is called a stratified sampling. So you use this, right? Stratified cross validation, all these things you used. But what this stratified sampling means is, suppose in the test data you are given this kind of a thing. Suppose there are some yeses in the test data, some of the instances, and there are some no's in the test data as well. Now we build strata from it. So building strata from it means you segregate the test data which are yes, and you segregate the data which are no. So we call each of these as a strata. So this is my strata 1. This is my strata 2. Now you can see that the randomization, random subsampling can also be used over this strata, that I take from here randomly 2 yes, I take from here randomly 2 no, and make my test data. Okay, this is how I can test. The other thing we can do, it may so happen that one of the problems, if you in the previous slide, we have seen that one of the problems maybe our test data is too biased towards certain classes. It may be many yeses but very less no. So in that case, it helps that I could generate repeatedly the same data while picking up. Right? Suppose I have 4 yes but only 1 no. What I will do is that I will pick up this random 4 data from here, or let's say this 2 no and 6 yes. I will pick up randomly yeses. I will pick up randomly 2 no's. But while I am picking up, I will just replace the picked up thing in the same sample itself, as if this sample set is infinite. So then this will be more, I would say the distribution of classes will be more clearly in the similar size, right? So this when we do this way, we sometimes call it as an oversampling. So when we oversample some less classes, we call it as an oversampling, or sometimes we need to undersample also if there are these many data. So we need to undersample, we sample less, we partition and arbitrarily take half of them and sample from them. So we do undersampling also. So you need not have to bother about all this because you are shown in a project with one simple function that do everything for you. So basically it does from the test data, what it does is that it builds strata and then randomly tries to generate your test vectors from it. Okay. So when you do this randomization with replacement, so here if I take a particular y and then cancel this one, then it's a stratified sample. If I take this y, also keep this y in my strata, then it's called a bootstrap measure. So just an extension of stratified sample, we call it as a bootstrapping. So these are basically, see, I mean, these are nothing to do about the theoretical side, that which one is good or bad. These are some of the methods people have used in estimation while computing their F1 score, precisions, and recall. This way people have tried to do their testing and it has proven well. There is no theoretical thing that this one is the best. So how good mix and match you can do with respect to the data sets you have, how good you can randomly sample, and how good you can do the randomization. Okay.
Sir, can you repeat the bootstrap?
Yeah. So see, generally from the strata, suppose in this strata I want to pick up two instances of ESS and two instances of no, you just pick up without replacement. That is stratified sampling. Bootstrapping is picking up with replacement.
Okay.
You sample with replacement.
So
Yes.
sir, if we put the same data in test and train data set, so I don't think that will increase the efficiency of model, because it's because we are using the same data to train the model and then we are testing it with the same data. So
No.
apparently the accuracy will increase, but
No. You will not do that way. See, you are given training examples, so you keep this data for testing. Do not use for training. You do not use this for training. These data you reserve for testing. Only train with this data.
okay. So in bootstrapping, like when we are doing oversampling, so you said that we'll treat it as infinite nodes, and then this YYNN, this the NN would be in both testing and training data. So if the NN is both in testing and training data, so
it's
it's
in the
already
testing data. No, not in the training data. All these stratas I form only with respect to only this position, the training set. The test set, not the training data by which I created the model. That you do not take anyway.
So you're saying that we are doing all this modification, all this stratified cross validation in the test data set.
Yes, in the test dataset, either the test dataset will be given to you as from the perspective of ground truths, which we call as ground truths, that we know the m number of test data, which what level it is, you test it according to the ground truths. Otherwise, suppose the ground truths are not available, then what you will do? There are many training data available. You keep a part of the training data as a test data. With the remaining part of the training, you actually do the training.
Okay, so
So by taking just one test data, we can generate a lot of distribution. Like accordingly, we can take the other samples too. So
no, but you can generate, but you do not know what will be the outcome class for that particular generation of test. Na? What is the actual function? If you know, then your job is done. You do not have to do machine learning. You do not know actual function. Suppose you know the test data T1. How can you generate test data T2 and its label also? You know test data T1 gives yes. How can you generate test data T2 along with its label? You cannot.
So, sir, how this is helping us? Like, if we are taking the sample out of it, like you told, we are just going to test on a particular sample, right? The method, I mean,
yeah, how is this helping?
Helping means?
Like what's the need of this stratified cross validation?
Oh, this is more randomized. I mean, this will help you because in other senses, see, all of them people used. So, and people try to see the efficiency of the model. And if it is a good model with a less overfitting and all, people try to find efficiency in all of these
So, but
cases.
if we can
This
generate other samples also, like you took
you
just
cannot,
2
because if you cannot generate other samples. See, if you can generate other samples, that means what? You know the function, the unknown function you should know. Then only you can generate. You cannot generate other samples from it. I am giving a very practical example. Suppose you know this level of this function, this level. Can you predict what is the level of in between this function? You cannot. It may be plus, it may be minus. So suppose you know this data, you know this data. You cannot generate in between something.
But we can, sir, but we can take the subset of it now, like you were taking, like
We
from one
took the
strata we are
subset of it.
taking. Yeah.
Yeah, we took the subset of it in terms of the training worth and testing classic. I mean, segregating that.
Okay, sir.
See,
Okay.
ultimately, your aim is that you need to have this number of test data in your hand. Let's say m number of test data.
So, but if we take other subset also, like maybe we are observing on subsets of say 1, 2, 3, and so on, and we do the accuracy measure, right? So according to distribution, it will give the different accuracy measure, right? Means the
Accuracy
distribution will.
for getting the accuracy measure, you need to know the actual class, actual classes of the data. So x1, yes, x2, no. All of them you need to know it. So either ground truth will provide you a set of test data, or if you do not have any test data, somebody gives you 1 million data with levels, you need to keep aside a fragment of such data to make your analysis tested. Otherwise, how can you test?
Sir, I got that point. Like we will
Yeah.
take the subset of the test data, and we'll observe on that. I'm asking if we take other subset also and we'll do the accuracy measure, then according to our subset distribution, the accuracy measure will change, right? Like if we, like the example you took over here, you took the 2y and the 2n, right?
Yeah, so the
What
other
if I take,
subset will do. So usually people do this multiple times, the stratified sampling.
yes, what,
Multiple times they do, and they finalize the average accuracy.
okay, okay.
So suppose this y1, y2 you have taken here, and some other samples give you y3 and y5 along with this, let's say n6 and n7, this sample, and take the accuracy from here. Yeah, people do that.
Sir, in a way, in stratified sampling, we are trying to uh,
Randomize, nothing else. We are
means
trying to randomize.
solve the class imbalance problem, right?
Yes, absolutely. We are trying to randomize and solve the class imbalance problem. That's it. Nothing else. All sort of this random subsampling, undersampling, oversampling, stratified are trying to solve the class imbalance problem. Because cost of misclassification is not always known to us. If this was known to us, then we could have used our traditional weighted formula to do everything, right? But this is not known to us always. So therefore, we need to balance between the classes to test. Okay,
Yes, sir.
good. So see, these are all empirical methods, right? People have used all of these and trying to find out whether their model is doing good in all of these estimates. That's what the claim is, nothing else, not theoretically that one is the best one. And as you can know, the randomization could not be you could not frame randomization formally that this randomization is the best randomization. Now, the third point, just to finish off, we need to know that how do we compare the models based on the metrics that you have estimated, and based on the methods through which you have you just collected data and try to see your metrics. So here one thing dominates, which is called as ROC, or receiver operating characteristics. Basically, this comes from the electronics domain, this ROC curve. So what does it try to do is that it tries to plot a particular data set with respect to false positive ratio and true positive ratio. So what does this false positive ratio and the true positive ratio is? That true positive ratio is basically the number of true positives divided how many positive actual class you are making true. So therefore, this plus how many positive actual class. So those which I am making false negatives are actually being positive classes, right? False negative. I am making false negatives. So they are positive. So how many of them are true positives? So as you can see, this is nothing but our recall, right? This is nothing but our recalls. And false positive ratio, if you do the same thing over false positive ratio, that the ratio of how many things I am doing false positive among all the positive cases. So that means how many true positives are there